Hello, everyone. So I'm going to jump straight in with my presentation now. Should be about 20 minutes, maybe a bit shorter. Happy to take questions at the end. Because there's a lot of technical information, I've scripted it. So I'm actually going to turn off my camera while I share, just while I read it, and then I'll come back on uh, at the end of the presentation for any questions. Text is a composed thing in the sense of an instance of language, of writing in the authorial sense, the composition of words and phrases and sentences to meaningfully communicate. Text is a composed thing also in being the product of multiple interconnected technologies and the result of a sequence of actions. This is true regardless of how text is instantiated, whether scratched in clay with a stick or wirelessly transmitted and displayed on your mobile phone. Text is a composed thing also in an oral culture, instantiated in performance at a particular place and time where, like the reader of a written text, the people gathered are part of the story. In this conference, we see exciting creative work in the typography of indigenous languages. This presentation is about what happens, largely invisibly, in the background of such work, the web of interconnected technologies which make it possible for text on digital media to be input, stored, transmitted, and displayed. It is about things that we mostly take for granted and that properly we should be able to take for granted, at least as writers and readers of texts. But the nature of these technologies is they were initially developed around the needs of settler languages and writing systems, English and other European languages. And while they've expanded to support hundreds of scripts and thousands of languages, at the margins of that support, things can get complicated. So it can be important for people working in language preservation and digitization of texts, and certainly for people making fonts or other software for indigenous languages, to have an understanding of these technologies and how they interconnect. This presentation aims to provide a basic introduction to just some of these technologies, providing a concise overview of some of the topics that will be discovered in a lot more detail on Sunday afternoon in the workshop on preserving languages in the digital environment. A digital text, like everything else on a computer, is just a sequence of numbers. At the lowest level, in the mind of the machine, where I hope most of you never need to peek, a text is a sequence of zeros and ones. Closer to the surface, where you might sometimes need to interrogate what is going on, especially if what you are seeing looks wrong when the text is displayed, the numbers are more likely 16-bit hexadecimal codes. I say more likely because older texts might be stored as shorter 8-bit codes, and text in some scripts, such as Osage, may be stored as longer 32-bit codes. Don't worry, that's about as complicated as I intend to get in this presentation. Each of these codes represents a character, which you can think of as an abstract unit of text. Characters can be letters, syllables, numerals, spaces, punctuation, mathematical or other symbols, or emoji. Where do these codes come from, and how does a computer know what characters they represent? Obviously, to be correctly interpreted across multiple different operating systems, communication protocols, and other software and hardware, these codes need to be standardized. This is the purpose of the Unicode standard, developed over the past 3 decades through the cooperation of major software companies, national standards bodies, publishers, academic organizations, and individual script and language experts. Unicode aims to provide a unique, unambiguous code for every character needed to encode, store, and transmit text in every writing system in the world. Before Unicode began standardizing encoding of characters using 16 and then 32-bit codes, text relied on a multitude of character sets that were each limited to 256 characters, sharing the same small set of 8-bit codes. Some of these were defined by national standards bodies, others by communications companies or operating system developers, and some by individuals or groups of people trying to find a way to compose and share text in a particular language. This is how many indigenous languages were first implemented on computers as far back as the 1980s, often using encodings invented by linguists working with the languages. We refer to these non-standard character sets as font encodings, because correct display of text depended on using a specific font or a special set of fonts with a common encoding. Because 8-bit codes were shared by so many different encodings, one always needed to be aware of which font to use, otherwise the text would display as gibberish. This became particularly problematic when transfer of digital text in emails, websites, and other electronic media became common in the 1990s. In the early 2000s, my colleague Ross Mills was working with the Inuit Government and Language Commission of the Canadian territory of Nunavut, developing some of the first Unicode encoded Inuktitut syllabic fonts. It was found that no fewer than 8 different font encodings were found to be in use by different communities in the territory and neighboring areas. Documents created using these disparate encodings needed to be converted to Unicode to be correctly displayed with the new fonts and to be suitable for publication in new electronic media. Unicode is what is known as a plain text encoding standard. This means that Unicode fundamentally is not concerned with what text looks like or how it is styled in a document, in upright or italic, in serif or sans serif font, etc. The code for the Latin uppercase A remains constant, regardless of how that character is displayed in a particular font. For some of the world's writing systems, this concept of plain text results in script encoding models that are fully abstracted from the graphical display of the writing system. Examples of these are Arabic and the various South Asian and Southeast Asian scripts that Unicode classifies as complex scripts, i.e. those that rely on higher level layout technologies in fonts and software to translate the plain text code sequences into readable text. An implication of this is that implementing script in a font requires understanding the particular model that Unicode has employed to encode the writing system. The good news for people working with indigenous North American scripts is that the model used for these tends to be relatively simple. For example, Unicode directly encodes full sets of graphical characters needed for syllabic scripts such as Cherokee and the various Canadian syllabic writing systems, meaning that the relationship between plain text and readable text is very close. Ironically, the Latin script orthographies of some indigenous languages can be much more complicated and challenging to implement. To understand why this is so, we need to look at the way in which Unicode encodes diacritic letters, or more precisely, how it encodes some diacritic letters, but not others. When the Unicode project began in the 1980s, several principles were established to guide decisions about what characters to encode. Some of these were high-level principles shaping the standard as a whole, e.g. that it would be a plain text encoding standard. But some were concerned with lower-level decisions that would affect whether individual characters would get encoded. And some of these principles are contradictory and result in apparent inequalities that introduce complications for some indigenous languages. One principle is that diacritics consisting of a letter with an accent, tone, or other mark, typically above or below, sometimes both, should not be encoded as precomposed atomic characters, but instead should be encoded as sequences of a base letter character followed by one or more combining mark characters. But another contradictory principle is that the Unicode standard should provide a one-to-one code mapping with pre-existing standard 8-bit character sets defined by national standards or in widespread use. So this meant that a lot of precomposed diacritic characters used in European languages were inherited into Unicode under this principle. The first 2 blocks of Unicode mirrors the coverage of the standard 8-bit ANSI character set for Western European languages, and many more European diacritics entered Unicode in this way. The existence of precomposed diacritics in the standard means that some characters in text could be encoded in more than one way, as the precomposed character, or as a sequence of base plus combining mark character. And software needs to know that these are equally valid and should be treated as identical for functions like text searching or sorting, what Unicode calls canonical equivalence. Now, remember that these inherited precomposed diacritic characters are exceptions to the principle that diacritics should be encoded as sequences of base letters with combining marks. Since their existence also requires additional work by software to keep track of canonical equivalence, other standards organizations, notably the Internet Engineering Task Force, asked Unicode to commit to not adding any more characters that have canonical decompositions. That is, to commit to enforcing the first principle regarding how diacritics should be encoded using combining marks. The apparent inequality this introduces is that diacritics for European and some other languages are encoded in Unicode as precomposed atomic characters, but the diacritics used in many of the world's languages, and notably in the Latin script orthographies of indigenous languages of the Americas, are not. Hence, indigenous peoples may ask, not unreasonably, where is this important character in our alphabet? Why hasn't it been included in Unicode? And the answer is that it is included, just not as a precomposed atomic character with a single code. This may look like a double standard, one rule for European languages and another for indigenous ones. But the goal of implementation in software, in fonts, in keyboards, and other input methods should be to make the distinction between precomposed and decomposed diacritics invisible, and hence the experience of indigenous users creating and reading text in their languages seamless and intuitive. This means, among other things, that those of us making fonts for indigenous languages do need to be aware of the distinction and to make decisions about how to handle decomposed code sequences at the point where the abstract characters become visible glyphs through our fonts. Here is the alphabet of the Hunkaminam language of the Musqueam First Nation, one of many Salishan languages in the region where I live. It is an example of a phonemic orthography that includes both precomposed and decomposed Unicode diacritics. The blue type forms, and I apologize to anyone with color blindness, are base letters atomically encoded, and the green type forms may be precomposed diacritic characters atomically encoded but with canonical decompositions. The orange type forms are diacritics encoded as sequences of base letters plus combining mark characters. As you can see, the orthography involves many digraphs, combinations of more than one letter to represent an individual sound, and software may need to treat these as units for sorting purposes. Looking at the repertoire of type forms in this alphabet, displayed as they are here, we can't know just by looking what mechanisms are used at the font level to display these decomposed diacritics. That is why I use the agnostic term typeform to describe what we're looking at, because each of these individual characters or sequences of characters may be represented by individual glyphs or by sequences of glyphs. So, for example, this diacritic typeform could be encoded as the sequence of the letter S plus the combining Karen. But it happens that this is also a diacritic in the alphabet of Czech, Finnish, and several other European languages. So it was inherited into Unicode as a precomposed character, unlike most of the other diacritics in the Hunkaminam alphabet. Hence, there are two valid and equivalent ways that this could be encoded, either of which could be displayed by a font as either a single glyph or a dynamically composed combination of base and mark glyph. In the workshop on Sunday, we'll go into a lot more detail about what the technical options are for deciding how to display decomposed diacritics, and we'll discuss the pros and cons of different approaches. For now, the important thing to note is what you might be used to thinking of as a cohesive letter in the alphabet might not be encoded in digital text as a single character, and in turn might be displayed by a font as one or more glyphs dynamically composed into what appears a single type form. Our primary engagement with the creation of digital text is often via a keyboard, whether a physical keyboard on a desktop or laptop, or an on-screen keyboard on a mobile device. Input methods are a vital part of the web of text, and because they are so central to the user experience of working with a language in the digital environment, their design is particularly important. I should clarify that when I talk about the design of keyboards, I'm primarily concerned with software, about the layout of the input methods and what happens when a user interacts with an individual key or sequence of keys, rather than with the hardware keyboard, which may in fact be used to input multiple languages and scripts. And most of what can be said about keyboards has parallels in other input methods, such as handwriting recognition or speech to text. In Sunday's workshop, my colleague Neil Patel will talk in detail about the design of keyboard layouts and their distribution to users as e.g. phone apps. The point I want to end with here is there is not necessarily a single correct way to input a given language. The image of people sitting in rows in secretarial school, all learning to type in the same way on the same kind of machine, is very different from the diversity of personalized preferences we might have in the ways we interact with our various digital devices. A keyboard layout can be designed to correspond closely to a user's mental conception of their writing system. For example, by having a single key input more than one character code, a decomposed diacritic sequence, for example, or even a digraph or other combination of characters representing a single sound. The best input technologies will also interact with editing functions, such as deleting characters or moving the cursor in the same way, respecting what the user thinks of as the orthographic units of text. Alternatively, a keyboard layout might use a dead key model, mapping from multiple keystrokes to a single character code, or could use a fully decomposed model, requiring individual keystrokes for base letters and combining marks. In the same way that the displayed type forms can be encoded as one or more Unicode characters, and these characters might be displayed using one or more glyphs in a font, the way those characters are input might involve one or more keystrokes. If all the parts are working properly, which is to say, if all of us involved in enabling people to textually communicate in their own languages have done our job well, then the web of text, like the web that Spider makes, is strong, but also flexible. Thank you.